Hello again. It's the online seminar series for OTFS SIG. And today we are very glad to have Professor Arman Farhang from Trinity College, Dublin, uh, to be here to talk about some recent advances in OTFS. And here is the some brief introduction of OTFS SIG, which is including the aims and the sponsors. And if you are interested in this special interest group, please feel free to join our mailing list and subscribe at this at this website. Okay, so without further ado, I'm going to introduce the main topic of today's speech. The topic is called Pathway Towards Practical Development of Delay-Doppler Multiplexing, and it's given by Professor Arman Farhang. I think in this talk, he's going to talk about the practical implementations, which is actually kind of missing in the current literature, and especially focusing on the Delay-Doppler multiplexing. I think it's a very interesting speech, and I'm going to give a brief introduction of the speaker today. Dr. Arman Farhang is an assistant professor in the Department of EEE at Trinity College, Dublin. He received his PhD in various communications from the Trinity College, Dublin, Ireland in 2016. Prior to this, he was assistant professor at Maynooth University and University of College Dublin in Ireland. He has published over 60 peer-reviewed international journals and conference papers, 4 book chapters, 1 edited book, and he holds 3 patents. Dr. Farhang is a principal investigator of multiple research projects around the broad areas of waveform design, multiple antenna processing, and reconfigurable intelligence services that are funded by Science Foundation Ireland under the Research Excellence Award, Frontiers for the Future and the US-Ireland Research and R&D Partnership Program. He is also a member of SFI Research Center's Advanced CRT and Connect as a principal supervisor and a founded investigator respectively, where he leads research around the topics of waveform design and multiple antenna systems for future various networks. The focus of Dr. Farhang's research team is on the design of novel physical layer technologies and advanced modulation schemes, plastered with multiple antenna solutions to provide high reliability, low latency, and scalability to various networks for the future. He is a senior member of IEEE and serves as an associate editor for EuroSIP journals on various communications and networks and networking since 2018. He has served in the organization committee of IEEE conferences and workshops such as the IEEE ICC 2020 and the IEEE ICC 2023 and 2024 workshops on OTFS and Delay-Doppler multi-carrier modulations for 6G. He regularly serves as TPC in top-tier IEEE conferences and workshops, in addition to being an active reviewer for several major IEEE journals. It's a very impressive CV, and without further ado, please join me to welcome Professor Farhang for today's speech. Okay. Oh. I'm stop sharing here. Thank you for joining us today.
It's a pleasure. So let me share my screen. Can you see the slides now?
Yes.
Okay, so yeah, today I'm going to talk about delay-Doppler multiplexing, as the title suggests. And there has been great interest and increasing interest in the topic in the recent years. But the main question here is if delay-Doppler multiplexing has a chance in future networks to be a part of future systems. And in this talk, I'm going to respond to this question in 3 parts. By first talking about the way to prepare the signal to transmit over the wireless channel. And then we will talk about how to find the received signal at the receiver, synchronization techniques, basically, and practical channel estimation and pilot design aspects. And finally, I will respond to the question by introducing a potential approach to making delay-Doppler multiplexing techniques a part of even current standards based on an observation in our team. So High mobility and high frequency communication systems are becoming more and more popular in 6G communication systems. Of course, the problems such as multipath and Doppler effects become more severe. For example, in high mobility scenarios, mobility leads to Doppler effect, and in high frequency communication systems, we use wider bandwidths, therefore the multipath become an issue, and also small mobility leads to more severe Doppler effects. Where using OFDM, we required constant channel estimation and tracking, which at some point is not sustainable, and we can keep up with the time variations of the channel. So to tackle these new generation of modulation techniques based on delay-Doppler signaling emerged and sparked by the introduction of OTFS back in 2017, and more recently, introduction of another waveform called orthogonal delay-Doppler division multiplexing modulation, or ODDM. So let's just move on to the first part, and just a couple of words about OTFS, and then focus on different pulse shaping techniques. So in OTFS, we place the data symbols. Let me turn on the laser pointer here. So we place the data symbols on a regular grid, delay-Doppler grid, with the delay spacing of delta tau and Doppler spacing of delta nu. We transmit this signal through the wireless channel, and the motivation for placing the data symbols in the delay-Doppler plane is that the wireless channel becomes, first of all, sparse and 2D almost linear time invariant in that domain. And therefore, as you see here, for example, with different windows, you may have leakage along Doppler, but if you use an appropriate pulse shape, the channel is quite sparse, and the same channel affects each data symbol on the grid in the same way. And on the top of that, the channel estimate provides a radar image of the wireless environment, and it shows different mobility profiles and also the delays which translate into the location of different obstacles and objects in the wireless environment. So OTFS implementation. In the first proposal of OTFS, OTFS was introduced as a pre-coding that can go on the top of any time frequency modulation technique. So if you consider in this overall, the whole talk, I refer to the number of delay bins as M and the number of Doppler bins as N. And OTFS in its initial proposal came as a two-stage modulation technique where the delay-Doppler domain data symbols were translated to the time frequency domain using a symplectic finite Fourier transform inverse, which basically is a 2D inverse Fourier transform that spreads the data symbols, each single data symbol, across the whole time frequency plane. Then it was transmitted through the linear time varying channel, and through the reverse operations, we would go to the delay-Doppler domain and estimate the channel that is 2D and LTI there, and equalize. So another way of implementing OTFS system is through ZAC transform, or ZAC OTFS, where the delayed Doppler data symbols are converted into the time domain, or the so-called delayed time domain, by using an inverse Fourier transform across the Doppler dimension. And then a cyclic prefix was added, and the signal is transmitted through the LTV channel, and through the reverse operation, we recover the received delay Doppler data symbols. And here it's very important to understand what we mean by delay time domain. It's all time domain, but the reason behind calling it this way is because of the presence of two different resolutions, delta tau, Doppler spacing, or in radar terminology, fast time, and the time duration or delay slot, delay block duration, which is T, which is comprised of M different delay symbols, or M delta tau. And we have N number of them. Remember, N is the number of Doppler bins here. And the whole duration of the OTFS block is N times T. So there are these two different implementations of OTFS, but to understand the waveform better and then get into how pulse shaping should be done, let us look into OTFS from a hybrid carrier perspective and consider only one Doppler bin here. The data symbols are placed only in one active Doppler bin, and the rest of the Doppler bins, we deactivate them. So we translated this signal, this delay Doppler domain, QAM data symbols, D00 to DM-10, to delay time domain by row-wise IDFT operation. And the result of this is repetition of each data symbol through the row-wise IDFT across all different time slots. And the same thing happens for all the rows. And as you can see here, the data symbols on each column gets repeated n times and scaled, of course, with this factor, which is the normalization factor. And what this means is that it's like we are repeating the same data symbols again and again. And to transmit this signal, we pass it through a parallel to serial block, and we form such a signal. So you see, these are the QAM data symbols that come one after the other, and they are repeated n times to combat the time selectivity of the wireless channel. So how to pulse shape this? From single carrier point of view, we use Nyquist pulses, and we scale them by different data symbols and overlap them by symbol spacing. And this signal is limited to a certain duration, starts here at this point and ends at this point. And this rectangular window here that limits the signal is quite important, as you will see shortly. So here, therefore, we have Nyquist pulses for pulse shaping. And if we look at different rows separately, for the first row, taking endpoint IDFT across this row to translate the signal to delay time is equivalent to just scaling each QAM data symbol by different tones. So this is similar to OFDM. In OFDM, we perform IDFT, and we modulate the data symbols through IDFT operation in the digital domain. So the first data symbol here scales the DC, as you can see here in the first delay bin, and the second one, the first tone. But at certain spacings, at equally spaced points, that as you can see here, these points are M samples away, so M times TS. So is the spacing between these points. And then we add them all up together to form the time domain signal. And these points are the peaks of the Nyquist pulses that we have. So as you can realize here, OTFS can be seen as a hybrid carrier waveform, as it's shown in reference 5 here. And it's single carrier along the delay, and it's multi-carrier along the Doppler. Therefore, for pulse shaping, we require a 2D pulse shaping technique. In one dimension, we pulse shape the signal along the delay dimension using the Nyquist pulses. And in the other dimension, as you see here, in multi-carrier systems, the signal starts at a certain point and ends at a certain point as well. Therefore, the pulse that is defined there is the so-called rectangular pulse, as in OFDM systems. So this rectangular pulse is quite important. This is the Doppler pulse shape, and these Nyquist pulses here are the delay domain pulse shapes. However, the sharp edges of this pulse lead to large side lobes in the Doppler dimension and lead to inter-Doppler interference due to the Doppler spread of the effect of the channel. And so this pulse along the Doppler, therefore, controls the level of interference due to the Doppler effect. And these short pulses along the delay control the out-of-band emission of the OTFS signal. This is a very important point to take note of. And to deal with these sharp edges, the classical approach in OFDM literature is to use a smooth pulse at the edges. And it's called a global window that is applied over the whole OTFS block to reduce the leakage and hence inter-Doppler interference due to the Doppler spread of the channel. And this global window was first introduced in reference 7 here, and also in reference 8 as well. So now I want to link these pulses to OTFS 2.0 and the pulse zones. So it's important to understand that these pulses along the delay just define the pulse zone in the delay time. Here, this graph shows the delay time signal. And if we take the Fourier transform across this, we go to frequency Doppler domain. And the so-called pulse zones along the frequency Doppler or frequency dimension are observed, as it's shown in reference 4. And these are called pulse zones for the reasons that become clear towards the end of this talk. Therefore, we form a 2D pulse in the Delay-Doppler domain by using these Nyquist pulses along the delay and such a smooth window along the time dimension, so that we can have predictability as is discussed in detail in reference 4. So now, how should we pulse shape our OTFS system? OTFS has two different implementation aspects. So one is through two-stage implementation, another one is single stage. So if we don't do oversampling and pulse shaping, these two approaches give exact same signals at the transmitter, at the output of the transmitter. However, when we start to do pulse shaping, they become different from each other. So one would think of doing pulse shaping using OFDM modulator in this first implementation approach. And we can say, okay, so we bring the signal to the time frequency domain, and then let OFDM modulator to deal with the pulse shaping. So in OFDM, interpolation and pulse shaping is performed by, after the delay Doppler signal is brought to time frequency domain, by zero padding across the frequency dimension. And this way we oversample the OFDM signal. And this can be thought of as just looking at this time frequency signal here, cyclically extend it, and then multiply it with a rectangular pulse or brick wall pulse, or maybe a Nyquist pulse. And if you use a rectangular pulse in frequency, along the delay, you won't have those short pulses because you have a sync pulse with large side lobe like this, as you can see here. And this is a problem. So to deal with this problem, we apply some roll-off in the frequency, which is a very well understood concept in single carrier literature for pulse shaping. So by application of this roll-off here and there, we reduce the side lobes of this sync so that we can truncate it and then achieve predictability for radar sensing as well. And of course, reduce the effects of fractional delay, because this pulse is quite important in dealing with the fractional delay shifts after we do oversampling, which happens anyways if we want it or like it or not. So this operation is equivalent to, this repetition is equivalent to upsampling in the delay time domain, by a certain factor, LUS, and then circularly convolving the resulting signal with a pulse shape. And because of this kind of pulse shaping, I call cyclic pulse shaping or circular pulse shaping techniques for OTFS, two-stage OTFS pulse shape. And here is the full modem structure for cyclically pulse-shaped OTFS, or CPS OTFS as we refer to it. So the problem here, though, is that we reduce the side lobes of the pulse along the delay, but we didn't reduce the out-of-band emission. To reduce the out-of-band emission after the signal is converted to the delay time domain, we can resort to classical OFDM techniques using windowing. So we cyclically extend the signal in time domain by adding cyclic prefix and cyclic suffix and multiplication with a smooth window in time to reduce the out-of-band emission. Another approach is to apply a certain number of guard symbols along the delay dimension here and there, as set them as 0, so that the circular convolution here gets slightly closer to linear convolution and smoothens the edges of the signal in each delay block, and hence reduce the out-of-band emission. So here, it's very important to consider how we add the cyclic suffix and cyclic prefix here, so that we can apply a window. So in OFDM literature, after oversampling, we would add a cyclic extension at each site and apply a window without any problem. But in OTFS, this is different, or when the channel is time varying, this is different. So when the channel is time varying, if for the delay time signal along the delay dimension, we cyclically extend the signal at two sides here and there so that we can accommodate a window, a smooth window. This is in the frequency domain equivalent to oversampling. So in this example, to make it clear, I use the same cyclic extension length as M here, the number of delay bins. And the effect of this is that we have 1 0 in between every other frequency sample in the frequency time dimension. And the problem arises here that when the signal is passed through the time and frequency selective channel, the time selectivity of the channel leads to the leakage of certain amount of the signal power to these 0 bins. And when we remove or discard the cyclic extensions at the receiver, we are removing the energy that has leaked to these oversampled bins, and therefore we lose certain part of the signal. So to avoid this, what we suggest doing is to do apply the cyclic extension before oversampling and interpolation here. And then we do interpolation by multiplication to this window. And at the receiver, we need to do match filtering with the pulse shape and then downsampling. So match filtering in the frequency is equivalent to multiplication with the filter again, and then downsampling is equivalent to aliasing, like here, as it's shown in this figure. And the full details can be found in this reference. So this is about the two-stage OTFS. But about ZAC OTFS pulse shaping, looking at this diagram, if the pulse shaping is applied here after the signal is brought to the delay time domain, we just bring it to delay time, pass it through a parallel to serial block, then upsample and pulse shape, convolve with the pulse. At the receiver, we do match filtering and downsampling, and we go to the then we go to the delay Doppler by row-wise DFT. So this leads to basically this, looking at these two structures, we can come up with a unified framework for pulse shaping on the delay Doppler plane. So in this framework that we have introduced in this reference 10, we look into different pulse shaping options using two-stage or circular pulse shaping and SIG OTFS space, which we call linear pulse shaping, by the way. And we can represent the transmit signal as the delay Doppler domain data symbols that scale different pulses. So these pulses are what's different for different pulse shaping techniques. For the circular pulse shaping, these pulses can be defined in this form. This function is a rectangular window that we have because of the cyclic pulse shaping. And the pulses, these pulses are shifted based on the delay index, which can be seen here in the time, and in the frequency based on the Doppler index. They are modulated to that Doppler frequency. But this pulse is not very simple and may lead to some issues when we have circular pulse shaping. For linear pulse shaping, it's much simpler. So as you see, the representation is the same within our framework, but the pulse is what's different. The pulse for linear pulse shaping techniques is shifted along delay and then modulated to the Doppler carrier, as you can see here. And for ODDM, what we found is very interesting, that there's subtle difference between SIG OTFS or linearly pulse-shaped case and ODDM. ODDM looks at OTFS as a pulse-shaped OFDM system. And here, these data symbols are scaling the pulse, ODDM pulse, which is defined in this form. It's very similar to linear pulse shaping, except an exponential term. And the difference arises in the fact that ODDM first modulates the pulse and then shifts the pulse along delay based on the delay index. And this leads to an interesting observation of a staircase property that we have shown in this reference 10. And therefore, we can represent the unified framework for pulse shaping using this structure, where we do have the delay Doppler data symbols. We upsample them, pulse shape them either circularly or linearly, and then bring them to the delay time domain, add them all up at CP, pass it through the channel, and then we perform the reverse at the receiver. And to implement this, we proposed a fast convolution-based technique in reference 10 again, where we show that we can achieve a large amount of saving in computational complexity in terms of complex multiplications. And the pulse, the delay domain pulse, should be truncated anyway, and this Q is the truncation factor that is defined in reference 10. If we don't truncate it, we may lead to issues in terms of fractional delay shifts. So in terms of complexity, as you can see here, as we change the truncation level, the complexity increases for the circular and linear pulse-shaped implementations. But with our proposed fast convolution-based solution, we are not sensitive to the Q factor or truncation factor. And in terms of the general complexity, what's interesting to observe here is that cyclically pulse-shaped case has the lowest complexity. In terms of out-of-band emission performance, ODDM and linearly pulse-shaped cases have the lowest out-of-band emissions, while OTFS without the windowing or anything has a spectrum very similar to that of OFDM that won't comply with this green curve here represents the spectral mask. Therefore, we need to either use the windowing techniques, but still windowing is not complying with the spectral mask. But with the use of a certain number of zero guards at each edge of the delay dimension, we can hugely reduce the out-of-band emission to an acceptable level. And addition of the zero guards help also in terms of bit error rate performance. So as I mentioned, if we for windowing and reducing out-of-band emission, if we apply cyclic extension before pulse shaping, so the performance won't be good because we lose a certain amount of signal energy. While if we do the in CPS or circularly pulse shaped OTFS, if we do add the cyclic extensions after before pulse shaping, we have better performance. And for all the different techniques, pulse shaping techniques, they get the same performance when we use certain number of zero guards at the edge of each delay block, or a certain number of the cyclic extension, which is like having a cyclic prefix, and therefore all the different techniques have the same performance. For uncoded case, for the coded case, the performance is the same, very close for all different techniques. These results are for 16 QAM on the right and on the left for 4 QAM. And this is all with the MMSE equalization, very simple equalizer. But when we use a more advanced equalizer, like the one proposed in reference 11 here, we can see that for uncoded case, compared to MMSE, we have huge amount of performance gain, around 8 dB performance gain, as you can see in this figure. Therefore, with advanced detector, you can get huge, even for uncoded case, huge amount of performance gain. So this is all about pulse shaping. If you are interested in the unified framework that we introduced in reference 10, please refer to our manuscript. So now we know how to transmit the signal. We need to understand how to find the frame at the receiver side, and you do synchronization, and afterwards doing channel estimation and equalization. So embedded pilot, the famous impulse pilot in OTFS, was proposed in reference 12, which can come into as two patterns: a pilot pattern with full guard along Doppler, which is quite robust to fractional Doppler case, or reduced guard, like this pilot pattern B. So now we want to find the signal, remember, at the receiver. So let's see how the signal looks like in delay time after we modulate it, or mainly the pilot, which we use for synchronization. This impulse pilot that is located at the Delay-Doppler bins MP, NP, gets a spread across the whole time dimension using endpoint IDFT. So this is a constant amplitude sequence with linear phase, that the linear phase depends on the location of the pilot on the along the Doppler dimension. So we want to use this for synchronization, and first we need to look at the received signal when it's affected by the carrier frequency offset, and it has certain amount of timing offset. And we want to estimate the timing offset and carrier frequency offset. So the first step is to just put the received signal on a grid and on a 2D, and form a 2D signal. And based on the 2D structure of OTFS block, the delay, the timing offsets will be translated into timing offset along the delay and timing offset along the time dimension. And in reference 6, we don't have any limitation on how much timing offset we have. No matter how much timing offset we have, we can find the location of the receive frame. So this is the way that different OTFS blocks look like in the delay time on a grid when we have cyclic prefix, and this is the pilot region. And this is the receive signal in a fully synchronous scenario. So here we form, in reference 6, we propose to form a 2D correlation function based on the received signal like this by considering a sliding window with length n number of time slots that spans across all the delay bins. And to find the timing offset along the delay, what we propose is to use this timing metric, which is nothing but adding all the samples on different columns for each row and finding its maximum and as we slide it, and finding the peak of this timing metric, we can find the timing, estimate the timing offset where we need to consider the position of the pilot, of course, and the length of CP to find this. And to find the timing offset along the time dimension, to find the location of this, the correct location of the whole window, we look at the second dimension or time dimension of the correlation function and sum up again across different rows and find the maximum of this to estimate the timing. And the details of this technique is can be found in reference 6. And here is a snapshot of the timing metrics to find the timing offset along delay for different Doppler spreads, static case, and I believe this is for 500 kilometers per hour case with 128 number of delay bins and 32 number of Doppler bins. And this is the timing metric to find the timing offset along the time. And with this approach, we can get quite an accurate estimate of the timing offset along 2 dimensions. And finally, we want to find the carrier frequency offset, which is quite tricky when the channel is time varying. When the channel is time invariant, we have remember a linear phase sequence that is a spread here. And therefore, the angle of the correlation function is has this phase, and then with subtraction of the linear phase due to the location of the pilot, we can find the carrier offset. But when the channel is time selective, some of these samples are just distorted, and therefore we run into a problem. And a very interesting approach that we used in reference 6 was to take advantage of the diversity that is introduced by the delay spread of the channel. So after we estimate the location of the pilot, therefore, we find the angle of the correlation function and sum the angles, average basically the angles across different taps of the channel, which repeat the pilot, but the carrier offset is the same. And therefore, using this equation, we can estimate the carrier offset. But still, this carrier offset is affected by the Doppler spread of the channel. So we cannot have super accurate estimates of the carrier offset. These are the results for pilot patterns A and B. And as you can see, the mean of error is only one sample, 1.1, let's say, sample, when we use the multipath diversity. And the variance is around 3 samples, which can be taken care of by around 3 samples, additional samples that will be added to the cyclic prefix, and therefore this error can be absorbed into cyclic prefix. And the mean square error performance of the carrier offset estimate is shown here. And so we, as I said, we cannot get super accurate estimate, but maybe accurate enough so that the users can pre-compensate the CFO and in the uplink align their signals so that the multi-user interference is reduced in the multi-user scenario. So, however, there are problems with this impulse pilot. So there are different types of pilot signals for channel estimation and synchronization on OTFS. Preamble-based pilots, which have problems due to channel age. Superimposed pilots, they have a problem of complex signal processing at the receiver. And embedded isolated pilots, they like impulse pilot, they suffer from large amount of peak to average power ratio. Therefore, and here is the problem, when we have this pilot, as you can see, as we increase the pilot power, the peak to average power ratio just goes astronomically high, and therefore we run into huge problems to the point that we cannot transmit a signal with PAPR over 20 dB. So what happens when we do IDFT across the rows is that we spread the impulse pilot power across the whole time slots. So if we want to reduce the pilot power, we may think of spreading the pilot power along the Doppler dimension, but this doesn't help us. Maybe using a ZC sequence, but this doesn't help us because IDFT already is spreading the signal here. Therefore, we thought about spreading the pilot power along the delay dimension and add some zero guard here on the top so that we avoid interference from data on pilot. But still here, there's some unused delay bins. So we can spread further the pilot power and then add the cyclic prefix at the beginning. And this is equivalent to very short OFDM-like symbol if we think about the delay time signal. For the impulse pilot, we send an impulse that is surrounded with some zeros, and therefore we just estimate, we sound the channel by looking at the impulse response. But when we have pilots with cyclic prefix, it looks like we are having very short OFDM-like symbols over which duration the channel is LTI. So we remove cyclic prefix, go to the frequency domain, estimate the channel impulse response at this pilot duration, and this pilot, and this pilot, and then we use the basis expansion to estimate the whole channel across the whole OTFS block. And with this approach, with pilot with cyclic prefix, we can dramatically reduce the PAPR of the signal. And for the impulse pilot with 40 dB power, the PAPR was over 20 dB. While for pilot with cyclic prefix, we can reduce the PAPR by around 14 dB here, or this pilot also helps to reduce the whole PAPR of the OTFS block with data. If we consider a full OTFS block that is loaded fully with data, the PAPR is 5 dB higher than the case where we have this pilot. So this pilot is quite interesting and useful. And here are the results in terms of the normalized mean square error for using the basis expansion. And as you can see, for the impulse pilot with basis expansion, we have the best performance, but the impulse pilot with the power of 40 dB that has very high PAPR, that essentially we cannot transmit this signal with such a high PAPR over the channel. While for pilot with cyclic prefix, the performance is good enough in terms of NMSE and the beta rate result of 4 and 16 QAM. You see there's a small amount of loss for pilot with cyclic prefix compared with the perfectly known channel. But this is quite negligible. And this is due to the energy that we remove by removing the cyclic prefix of the pilot. And for channel estimation, this pilot it's a Zadov-Chu sequence. So when we take IDFT across the row, we have periodicity still that can be deployed to estimate the timing offset by using a sliding window across the delay dimension and another sliding window across the time dimension to estimate the timing offset and find the location of the OTFS frame at the receiver. And the carrier frequency offset can also be estimated as it's shown in reference 14. And compared to the impulse pilot of reference 6 here, we have even more accurate estimate, carrier offset estimate, which is quite important when it comes to multi-user scenarios, because each user needs to pre-compensate the CFO first and send the signal to the base station. And for the timing offset, we have a pretty good result. So this is how we do synchronization with a practical pilot called pilot with cyclic prefix. And now after doing synchronization and pulse shaping, now I'm going to finally answer the question about how we can make delay-Doppler multiplexing techniques a reality in future communication systems. So just let's consider different domain translations. So we have delay-Doppler, frequency time, and delay time dimensions. So in ZAC OTFS, we take IDFT across the Doppler to take the signal to the delay time, or in general, time domain. And in two-stage implementation, we take DFT across the delay to take the signal to frequency Doppler, and then another IDFT along the Doppler to take it to time frequency. And then we use a time frequency modulation technique such as OFDM to take the signal to the delay time domain. So these two IDFTs can be, based on Kulitake's theorem, can be implemented using a very large DFT across the frequency Doppler, because frequency Doppler essentially is frequency domain with two different resolutions. So we take a large IDFT to take the signal to delay time domain. So just now paying attention to this DFT along the delay, this can be thought of as a DFT precoding, and this is a large IDFT to take the signal to delay time. Therefore, we can implement OTFS using single carrier FDMA. And from the manufacturer's perspective, this is very important, which enables low-cost implementation of OTFS, even without the need for changing the current 4G, 5G standards, at least in the uplink. And estimation and detection techniques for OTFS, therefore, can be applied to single carrier FDMA and vice versa, which is quite an important result. And just to take a closer look, let's consider ZAC OTFS modulator, where we take IDFT across each row of the delayed Doppler grid, and then we upsample by factor of m, circularly shift, add the signals, and add SIG finally. So if we consider these two blocks, IDFT and upsampling, this is equivalent to making this signal DMs periodic, repeat them basically m times, and taking IDFT across them to get the signal at the out. And this circular shifts in the frequency domain here. They are just some phase multiplications, which lead to some factors here, which we call tweedling factors, DFTs. And then we interleave the output of this DFT here. And these are nothing but the data symbols in one Doppler bin, but all the delay bins. And we can implement OTFS modulator in this form. So if we forget about these phase factors here, this is nothing but single carrier FDMA or DFTS spread OFDM with interleaved subcarrier allocation in the frequency. And that's what gives us the diversity gains. And for the demodulation, we do the reverse. Again, these two blocks can be replaced by the downsampling here is aliasing. That's why we have aliasing here. and endpoint DFT becomes endpoint DFT. And based on this, which results are detailed in reference 15, we can form the OTFS demodulator in this shape, where again, these phase factors here, tweedling factors, are basically what we need to implement OTFS using single carrier FDMA architecture, which is already existing in the current standards. This is very important, which enables us to implement delayed Doppler multiplexing in the even 4G standard. And here is the channel effect difference between OTFS and single carrier IFDMA. The channel for both systems, if we look at the channel from the perspective of before DFT precoding and after IDFT post-processing at the transmitter and receiver respectively, the channel is in delay Doppler. But the only difference is just some diagonal matrices that are multiplied from left and right. And these don't change the absolute value of the channel. So in absolute value, these two channels are equal. And they are only in different in phase and non-phase. So my conclusion here is that we can use single carrier FDMA to implement delay Doppler multiplex. For synchronization, the same, if we use the same pilot, we can do synchronization using the correlation-based techniques. Here, I just, for the sake of simplicity, we use impulse pilot. So we could synchronize both systems, and however, with the impulse, the maximum peak that we found out, the maximum peak is not the essentially right timing, because that's dominated by the maximum tap of the channel. So we came up with a new contribution here in terms of synchronization, which is applicable to both OTFS and single carrier FDMA, where we don't look at the maximum peak, because the maximum tap of the channel is not necessarily the first tap. And therefore, we define the threshold. So we find the maximum tap. We just look at the previous taps before that, which can lead to more accurate timing offset and carrier offset estimate. So compared to the previous solution for impulse pilot. So here, as you can see, the timing offset estimate is, we will have one error in 1,000 OTFS blocks. So the probability of timing offset error is pretty low with this very simple thresholding approach. But for what's interesting is that for both systems, we get the same result for synchronization. And for channel equalization, for OTFS, we do delay Doppler domain equalization or cross domain. But for single carrier systems, we always used frequency domain equalization here. Here we, in our work, we propose to perform equalization after the IDFT post-processing unit. And therefore, we can get exact same results for both systems. So another important aspect here is the resource occupancy. If we consider these two structures for OTFS or single carrier FDMA, it doesn't matter, we can find out about resource occupancy. This structure for each data symbol on the, if you consider the delay Doppler plane data symbols, each of these symbols are represented with different color. For example, the yellow one represents the delay Doppler bin 0, 0. And if we look at this structure, taking IDFT across the rows will repeat this n times, as we can see here, using this structure. How about using this structure? This shows the frequency Doppler location of each data symbol. So if we consider D0, 0, and the rest of the data symbols are 0, so this endpoint DFT will repeat them and places them in unequally spaced points are along frequency Doppler. And here we are, it's important to note that we are in frequency Doppler. And therefore, this represents the resource occupancy in the frequency time. By time, I mean delay time. So these pixels in this picture are spaced by delay spacing, and each block of M samples represents one time slot. In the frequency, each pixel represents a Doppler symbol, and n number of them, a block of n number of Doppler bins represents one frequency or frequency spacing. So this is frequency Doppler dimension. And interestingly, these points here are the peaks of the pulse zones that are shown in OTFS 2.0 paper. Finally, what's important to note is multi-user aspects. So based on this resource occupancy and the repetitions, for example, if we allocate certain number of delay Doppler bins to different users, U0 is user 1, U1 is user 2, U2 is user 3, we know how the time frequency resources are occupied. And this is nothing but the tile structures of OFDM system. And therefore, this means that we can do delayed Doppler domain multiplexing by using the same resource blocks that exist in current standard and do delayed Doppler multiplexing without even the need for changing the standard if we consider these spacings as the subcarrier spacings in 4G and 5G systems. Therefore, this is quite promising in my view and can make delayed Doppler multiplexing a part of current wireless systems as long as we use the interleaved resources in both time and frequency. So a high mobility user can request those resources and use them, or the base station can allocate those resources that are interleaved in both 2 dimensions to the high mobility users. And in our paper, reference 15, we provide the formulation for multi-user input-output relationship for multi-user scenario using defining a compound channel matrix, which is formed by the columns of the channel matrix that are allocated to the resources that each user occupies. And one last point I would like to emphasize based on this structure is that OFDM came by saying that, okay, I will break the frequency selective channel into different parts where the narrow bands where the channel is almost flat. And OTFS is 2-dimensional form of OFDM, which does break the channel into very narrow bands where the channel is frequency selective channel becomes flat over each Doppler subcarrier. And it interestingly does that along the time as well. So these delay spacings are very short. So the channel is broken into multiple delay blocks here where the time variations of the channel can be considered as none. So over each square here, we can consider a completely flat, almost flat channel. And this is very important point that emphasizes the potentials of OTFS. And it's like OFDM, but OFDM just breaks the channel into narrow band channels in the frequency domain, not in along the time dimension. So if the channel varies across the time, it's time selective, OFDM fails. But here OTFS has 2. It breaks the signal, the channel into narrow pieces, both in time, in frequency and time, and spreads the signal across multiple time slots so that at the receiver, when it combines them back, it takes a full advantage of the time diversity, and the same for frequency. And this is quite important point that I thought needs emphasis. So To conclude the first part of the talk, it's important to look at delay-Doppler multiplexing from hybrid carrier perspective. It helps us to understand the waveform better in more simpler way that we read in even very old textbooks. And from implementation point of view, there are very subtle differences between different pulse shaping techniques for delayed Doppler multiplexing techniques. And finally, the choice of delayed Doppler pulse shaping filters is quite important in combating the effect of fractional delays and Doppler effects. And we all have seen that in OTFS 2.0 paper where predictability becomes very important, and that emphasizes on the use of delayed Doppler domain pulse shaping filters. Or even in ODDM paper, you can find very interesting insights into the pulse orthogonal delayed Doppler pulse design. And there are other colleagues that have also very recent contributions along this dimension. So we need to do more research along the pulse shape design in the delayed Doppler. And for part two, we use the 2D correlation metric for timing recovery. And from implementation point of view, the widely used impulse pilot is not practical. We cannot send a signal with very high peak to average power ratio due to very strong pilot. The pilot gets clipped, and if you want to implement the system, you lose the pilot. You cannot find it. And therefore, more practical pilots like pilot with cyclic prefix should be considered and looked into. And most works around synchronizations are only applicable to single user downlink scenario. However, nowadays there's no system that is single user. So we need to do more research on multi-user synchronization, which is quite important because for example, if you think about frequency offsets that are uncompensated in the uplink, one may think of absorbing them into the channel, but doing so will lead to a user with carrier offset appearing as moving in much higher velocities than OTFS can handle. And about single carrier FDMA part 3, delayed Doppler multiplexing, we saw that it can be achieved by using the currently existing technology, single carrier FDMA and current wireless standards. And when single carrier FDMA is utilized though, what we need to bear in mind is that the equalization should be performed after the IDFT post-processing at the receiver. And finally, from multiple access point of view, it's important to explore waveform processing techniques that allow for delayed Doppler multiplexing using single carrier FDMA in a multi-user setup. And finally, I'd like to acknowledge the hard work of my PhD student, Mohsen Bayat, and the postdoctoral research fellow in my team, Dr. Sanup, who have been working on the pulse shaping and synchronization aspects, and also single carrier FDMA. And I would like to also acknowledge Science Foundation Ireland for supporting the work we are doing. And finally, I'd like to take this opportunity to advertise a postdoc researcher position on the practical aspects of OTFS that is currently open in my team. And please contact me if you have any questions or if you are interested. Thank you so much for your
Thank you. Thank you, Arman. That's a very informative and a great presentation. I personally enjoy it very much because you talk about so many like practical aspects that has not been discussed previously in detail. So I like this very much. We have several questions, and I hope if you have time to answer them.
Of course, yes.
Yeah, we have a question from Costas typed in the meeting chat. He was asking that you have mentioned that in OFDM systems, we probably need frequent channel estimation. in the fast time varying channel, but why we do not need this in OTFS?
So yeah, in OTFS, we don't need to use as many pilots as you need in OFDM systems because we use delayed Doppler domain signaling. So we put one
Right,
pilot, but it gets repeated in the
right.
block.
Yes. I think that's basically the explanation for this question. And oh, we just have another question from David. Uh, in the multiple access part, users were orthogonally multiplexing the delay-Doppler domain. Does the channel breaks this orthogonality? If so, is it required to decode and equalize the users jointly?
So yes, basically the orthogonality here is broken. And in this equation, we have that, the details of how it's broken due to the different
Right.
Doppler shifts. And if we can estimate accurately the compound channel matrix, then we can combat that effect.
I think that's a very good point. And I remember there are papers also talking about this, like if you somehow locate your resources for each user in a special way, sometimes you can still mitigate the multi-user interference, or like you treat the interference within each user. I think there are two ways to do this as well.
Of course, yes, there are works I've seen that have some certain pattern in terms of the
Right.
allocation of the resources to different users.
Hmm.
But here in this format, we can allocate the resources in generalized form to different users. There's
Right.
no limitation on that.
I see. Right. Great. Okay. I have also collected some questions from the audience who have privately sent it to me. And the first one is about the post shaping, actually, where you mentioned for this SFT-based post shaping, and there is a global window that you applied in one of your previous slides.
Yes.
And yeah, that's actually also one of my own questions because I'm really interested in this. Uh, what if you are having some, for example, cyclic prefix, and you are using a smoothed window, not the exact rectangular? Will that affect this cyclic prefix structure when the window is not perfectly rectangular?
So you mean this kind of global
Yes,
window, right?
yes,
So
global window, yes.
of course, the cyclic prefix that we add, the cyclic extension is
Hmm.
like this signal, this part that you cut it. So
Right,
this part should be added here so that at the receiver we can recover the signal.
right.
So, or in other words, whatever you have inside this rectangular window
Hmm.
gets periodically repeated. You can consider it as a periodic signal from minus infinity to plus infinity.
I see, right.
And that way you need to consider that to add the cyclic prefix.
Right, right. That's a good point. And also, in addition, I wonder, for example, if we consider standard OTFS structure, you have what M delay bins and N Doppler bins, and eventually in the time domain, you're supposed to have what M N samples to transmit. But
Yeah.
after adding CP, you have some additional samples due to the CP. So this global window you are talking about, does that should be aligned with the length that including the CP length as well, right?
Yes, it should be.
Then will that affect the orthogonality in the delay-Doppler domain?
So the orthogonality, not really, because if we consider this signal as periodic signal, it's like a sine wave. If
Right.
you look at here, so in like we should think about it as OFDM system that
Hmm.
we know very well. So
Hmm.
this sine wave can continue to infinity from plus infinity and minus infinity.
Right.
When we add the cyclic extensions, we
Hmm.
just widen our window, and that does not affect the orthogonality after we remove, of course, the cyclic prefix.
I
But with
see.
the cyclic prefix, you don't have a full period, so orthogonality is
Hmm.
affected.
Hmm. That's a good point. Thank you for the answer. Okay. Uh, so I think there's another question regarding the post shaping. It's about there was one picture you mentioned that you add CP after post shaping, right?
Yes.
So I assume here that you are working on discretized post shaping that convolved with the samples of the post. Yes. Uh, so then my question is actually, what is the chirp pulse you are using here? Will that also affect the performance? For
So
example, mhm, yeah,
here we use the Nyquist pulse, right?
right. Yeah, I mean the Nyquist is possible like when you after adding the CP, so you using, for example, something like a sync pulse to transmit, right?
Yes.
I see.
The point is this addition of cyclic extension after pulse shaping or before it. So here I needed cyclic extensions at the edges of each delay block
Right.
to be able to accommodate smooth edges of the window. So
Mm,
in OFDM literature, we do this after interpolation, after zero padding in a frequency.
right.
But here, if we do that, when the channel is time varying, my point is that by addition of these cyclic extensions, you are
Mm,
doing some sort of interpolation in the frequency domain
right.
that I
Right.
showed by addition of the cyclic extension equal to M prime
Mm,
here.
I
And
see.
so that this is equivalent to addition of 1 0 bin in the frequency Doppler. And when
Mm,
the channel is not diagonal here, when it's time selective, you have leakage to these. And
right.
after you remove the cyclic extensions, you're removing these leakages and you lose a part of signal energy.
I see. Right. Thank you for the answer. And also another part of this related to the post design is that you mentioned your order to reduce the out of band emission that you can somehow add some zero guards along the delay dimension.
Yes.
Uh, I wonder if this will give you some rate loss because you are not multiplexing symbols there.
Yeah, it's like we are considering here reduced CP OTFS.
Right.
If you compare with full CP OTFS here,
Hmm.
we don't need a large number of zero guards. With around,
I
I
see.
believe in the results that I showed here, I think with around 3 0 guards on each side of the delay dimension, we can
Right.
get huge reduction here. And
I
there's
see.
no other way around it because you have cyclic convolution or circular convolution that is limited by a rectangular window.
Hmm.
These zero guards brings that cyclic convolution to somewhere in between cyclic and linear convolution. So you have
I
a
see.
smooth edges on the
Right.
side.
Right, that's very interesting. And speaking of that, I remember there was a paper from Chokes. He was talking about that the PAPR issue for OTFS in general, that is actually proportional to the number of Doppler bins instead of delay bins you have. But here you are adding zeros in along the delay dimension. I wonder, do you have any intuitive explanation for this kind of difference?
Okay, so if your question is if we add zeros, the PAPR gets increased. Is that it?
No, I mean like intuitively for me, what I understand is like the PPR of OTFS relates to how many Doppler bins you have. But
Of course.
here
Yeah.
you are not reducing the Doppler bin, you are actually reducing the delay bins, if I understand correctly.
Yeah,
So
no, I'm just setting inactivate some delay bins
exactly, yes, right.
so that
Yeah.
we can reduce out-of-band emission. But what in Chok's paper is talked about PAPR is
Uh-huh.
that when you have a multi-carrier system with,
Mhm.
let's say, n number of subcarriers, he's talking about the multi-carrier dimension here.
That's right, yes.
And this defines the PAPR. In single carrier case, along the single carrier dimension, we don't have any issue because the
I
delay is
see.
single carrier dimension.
I see. That's a good point. I see. Right. Okay, thank you. Let's move on to the second part of your talk. And I received a question regarding this the synchronization with respect to the CFO and the time offset as well. Uh, People are saying that because OTFS is shown to be robust to this kind of delay and the Doppler shifts, I wonder, so therefore they're asking how stringent this synchronization requirement will be if we consider the inherent robustness of OTFS.
Mhm. When you consider single user scenario, you can absorb all these effects into the channel because
Right.
the channel, the carrier offset is absorbed to the Doppler shift. and
Right.
Doppler spread.
Yes.
But the problem there is that it adds up to the Doppler spread, the
Mm-hmm.
CFO. If you don't estimate or pre-compensate, especially in the uplink of a multi-user system, then the CFO is like additional velocity. So OTFS is known to lose its advantages when you go to higher speed, very high speeds.
Okay.
So
Yes.
this is like if you are moving with 100 kilometers per hour, you have large amount of CFO,
Mm.
your speed appears as 1000 kilometer per hour. So
Mm.
then we will face issues if you don't compensate them.
Okay. Thank you very much. Okay. So the final questions are about this pilot design you are talking about actually. Um, So when you are applying this uh zero padding and cyclic prefix to the pilots, will that affect the channel estimation performance because you are introducing potential interference among the pilot symbols if you are talking about this cyclic prefix, right?
And there's no interference because when we take, this is delayed Doppler representation. When we take
Mm,
this delay time, we take IDFT across each row.
right,
So we're spreading each value here across the whole time dimension.
right.
This is
Uh,
equivalent to transmitting a short symbol here, another short
mm,
symbol here, and another short symbol here.
I see.
So there's no interference from data on pilot, but at the end here, there is, because we don't use any guard, there's
Hmm.
interference from pilot on the data. So we need to remove the pilot first
Right.
for detection.
Uh, If I understand correctly, if you are talking about the delay-Doppler domain representation of the pilot pattern you showed previously, because in delay-Doppler domain is a convolution instead of a multiplication. Therefore, while that, for example, in the picture on the right-hand side, will that give you some interference along different pilots?
Well, after we remove it in delay time, because we remove the pilot in
I
delay
see.
time,
That's a good
that
point. Yes.
interference is removed. So there's
Okay.
no problem with that. So here in the results that I
Right.
showed, in this structure, I talk about pilot removal, as you
Mm-hmm.
see.
Mm-hmm. I
And
see.
after pilot removal, this is the beta rate after
Right,
estimation.
right. That's a very smart. So, but at the cost you lose a little bit like a pilot power, right? Because
Yes,
you
because
remove
of
something.
CP, because of CP, yes.
Right, right. Okay, that's a very interesting point. And the also there are some questions regarding the equivalence of OTFS and the single carrier FDMA. Personally, I found this is very interesting and have not been discussed very much previously. Um, so I just have a very high level question regarding this. You show there in terms of the channel matrices, they are quite similar. In,
Yes.
in except for that you have two diagonal matrices. Uh, yes, that equation. So I wonder, does that also somehow showing that in single carrier FDMA, you're supposed to have a full diversity, like what OTFS has?
You do because we have interleaved allocation. So
Right.
this dimensions frequency Doppler.
Mm-hmm.
So if you look at the OTFS2 works, you see the pulsons in frequency Doppler. So
Mm-hmm.
the data that you put here are put on the peaks of the pulsons. So it's the same thing. That's all I'm talking about
I
here.
see.
A very small difference of these phase shifts that don't have any effect
Mm-hmm.
on the performance.
Right.
That's why
Right.
you get the same performance for both systems.
Right. I agree with you. And you are also mentioned that when you are doing detection, for example, for single carrier FDM, you should do it after the the IFFT part, right?
Yes.
I wonder why is this? I mean, intuitively, I would think because this IFFT is a unitary transform, it should not affect the detection performance.
Yeah, no, you can apply cross-domain also equalization here.
Right.
So here, the what I'm saying is that I'm just referring to very simple detector like even MMSE or message
Okay.
pass. that if you want to apply the exact same techniques, you should apply it
Ah, I
here.
see. Right.
But another important aspect here is that by using single carrier FDMA structure, you won't have the lowest complexity for the modulator and demodulator because compared to ZAC OTFS. But
Right.
here, this structure gives you immediate access to frequency Doppler and delay Doppler at the same time, and you have delay time before it. So you have immediate access between different domains. So you can do cross-domain
I
equalization.
see. Right. Yes, that's very interesting. Thank you for the answers. I think we just received one last question from the audience, which is actually talking about the synchronization. I think what he wants to say is the synchronization normally aiming for the path with the maximum channel gain. However, uh, in some cases, this maximum channel gain may not be able to received. Will that be uh, will that give some practical issues for the synchronization?
Yes. So in the first work we did with impulse pilot for synchronization, we showed how to exploit the full diversity gain of the channel and use
Right.
the receive power from all the channel path
Mhm.
to improve the estimation accuracy.
I see.
Definitely, that should be exploited.
Yes. Okay. Thank you very much. I think we have covered all the questions, and this is a very great presentation. And thank you again for being here today.
Thanks very much for having me.
No, it's a pleasure for us. And just one additional term is like that Professor Farhang is recruiting new postdocs. I think it's a great opportunity. If the audience have uh, are some interest, please contact Arman directly. Thank you.
Yeah, thanks very much. And do spread the word if you know
Of
interesting,
course,
interested researchers in joining our team.
of course.
Definitely
Yes.
fantastic. All right.
Okay. Thank you again, and see you next time.
See you.
See
Bye-bye.
you. Bye bye.